Many individuals enter the electrical trade with licenses or apprenticeships, but without a solid foundation in core electrical concepts. A lack of understanding of fundamental areas such as box fill calculations, voltage drop calculations, conductor sizing, and grounding and bonding principles may be observed. Incorrect installation practices and misconceptions can be passed down from experienced electricians to apprentices. If these beliefs are not challenged or corrected, errors are perpetuated. Apprentice schools sometimes inadvertently reinforce incorrect techniques because of inadequate instruction. Resistance to accepting mistakes and embracing new perspectives may hinder professional growth and improvement. Some individuals may be hesitant to acknowledge gaps in their knowledge or challenge established practices. Pride can prevent individuals from seeking out opportunities to expand their skill sets. These observations reflect a trend in the electrical trade. It can be estimated that a minority of electricians, less than 10%, demonstrate a strong commitment to continuous learning and embrace new ideas. Several factors might contribute to these challenges. Firstly, lack of formal training or incomplete apprenticeship programs are a major factor. Secondly, industry complacency and acceptance of substandard work can be observed. Thirdly, limited opportunities for professional development or continuing education are present. Fourthly, lack of mentorship or guidance from experienced electricians is also a possible cause. These issues can lead to compromised electrical installations and potential safety hazards. Inefficient use of materials and labor can result in increased costs. The industry might experience stagnant innovation and development if the workforce is not adequately trained. Career advancement for individuals with limited knowledge can be hindered. Several solutions can be implemented to address these issues. Firstly, strengthen apprenticeship programs and ensure comprehensive training. Secondly, promote continuous learning and encourage questioning of established practices. Thirdly, provide opportunities for mentorship and professional development. Fourthly, enforce stricter quality control measures to prevent improper installations. It is essential to understand box fill calculations. The National Electrical Code, or NEC, specifies requirements for the number and size of conductors and devices permitted in electrical boxes. Proper box fill is crucial to prevent overheating and ensure safe connections. NEC Section 314.16 provides detailed guidelines on box fill calculations. The number of conductors, device yokes, internal cable clamps, and equipment grounding conductors contribute to the total box fill. Each conductor is counted based on its size. For example, a number 14 American wire gauge or AUG conductor counts as 2 cubic inches, while a number 12 AWG conductor counts as 2.25 cubic inches. Device yokes, such as switches and receptacles, count as 2 conductors based on the largest conductor connected to them. Internal cable clamps count as 1 conductor based on the largest conductor entering the box. Equipment grounding conductors count as 1 conductor based on the largest equipment grounding conductor entering the box. If the box contains different sized conductors, the largest conductor size determines the deduction. To calculate the total box fill, sum the cubic inch volume occupied by all conductors, devices, clamps, and equipment grounding conductors. Ensure the total cubic inch volume does not exceed the maximum volume marked on the electrical box. Now let's discuss voltage drop calculations. Voltage drop refers to the reduction in voltage that occurs as electrical current flows through a conductor. Excessive voltage drop can cause equipment malfunction, overheating, and reduced efficiency. NEC Section 210.19 AM provides guidelines for voltage drop in branch circuits. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. To calculate voltage drop, use the following formula: voltage drop equals current times resistance. Resistance depends on the conductor's material, length, and cross-sectional area. The formula for resistance is resistance equals resistivity times length divided by area. Resistivity is a property of the conductor material. Copper and aluminum are commonly used in electrical wiring. Length is the distance the current travels, and area is the cross-sectional area of the conductor. Use the appropriate units for each variable. Current is measured in amps, resistance in ohms, length in feet, and area in circular mils. After calculating the voltage drop, determine the percentage voltage drop using the formula percentage voltage drop equals voltage drop divided by source voltage times 100. Ensure the calculated voltage drop does not exceed the recommended limits. If the voltage drop is too high, increase the conductor size to reduce resistance. Consider using copper conductors instead of aluminum, as copper has lower resistivity. It is important to select conductors based on their ampacity. Ampacity is the current carrying capacity of a conductor expressed in amps. Conductors must be sized to handle the anticipated load without overheating. NEC section 310.15 provides ampacity tables for various conductor types and insulation ratings. These tables consider factors such as ambient temperature, number of conductors in a raceway or cable, and the type of insulation. The most common insulation types are THHN, THHW, and XHHW. THHN is suitable for dry and damp locations, while THHW is suitable for wet locations. XHHW is suitable for dry and wet locations and has a higher temperature rating. To determine the appropriate conductor size, first calculate the load current. For a resistive load, the current equals power divided by voltage. For example, if a 2400 watt load is connected to a 240 volt circuit, the current is 10 amps. For motors, consider the motor's full load amps, or FLA, rating. Refer to the motor's nameplate for the FLA value. After determining the load current, refer to NEC table 310.15 to select the appropriate conductor size. Apply any necessary correction factors for ambient temperature or the number of conductors in a raceway. For example, if the ambient temperature is higher than 30 degrees Celsius, a correction factor must be applied to reduce the conductor's ampacity. If multiple conductors are bundled together in a raceway, a derating factor must be applied. Ensure the selected conductor's ampacity is equal to or greater than the adjusted load current. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, causing the overcurrent protective device to trip. Bonding ensures all metallic parts are electrically connected, minimizing voltage differences and reducing the risk of electric shock. NEC Article 250 provides detailed requirements for grounding and bonding. The grounding electrode system typically consists of a ground rod, ground ring, or metal water pipe. The grounding electrode conductor connects the grounding electrode system to the equipment grounding bus in the service panel. Equipment grounding conductors connect non-current carrying metallic parts of electrical equipment to the grounding system. These conductors provide a path for fault current to return to the source. Bonding jumpers are used to connect metallic enclosures, raceways, and equipment to ensure electrical continuity. Main bonding jumpers connect the grounded conductor to the equipment grounding conductor at the service equipment. Supply side bonding jumpers connect metallic parts on the supply side of the service equipment. Load side bonding jumpers connect metallic parts on the load side of the service equipment. Ensure all grounding and bonding connections are secure and properly sized. Use appropriate connectors and grounding bushings. Regularly inspect grounding and bonding systems for corrosion and damage. It is crucial to understand the differences between grounding and bonding. Grounding provides a path for fault current to return to the source, while bonding ensures electrical continuity between metallic parts. Both grounding and bonding are necessary for electrical safety. Lack of understanding these principles can lead to dangerous installations. There are implications of compromised electrical installations. Firstly, there are potential safety hazards. Secondly, inefficient use of materials and labor is seen. Thirdly, stagnant industry innovation and development can occur. Fourthly, hindered career advancement for individuals with limited knowledge can be an issue. Solutions to these challenges include firstly, strengthening apprenticeship programs and ensuring comprehensive training. Secondly, promoting continuous learning and encouraging questioning of established practices. Thirdly, providing opportunities for mentorship and professional development. Fourthly, enforcing stricter quality control measures to prevent improper installations. These measures help to ensure a safer and more efficient electrical trade.